The goal today is to have a more practical thing. That's why this is a workshop and not just a general presentation of Bayesian methods. It's actually useful for me to ask people if you have already used the typical mixed effects model in R or Python or something like that. Okay, good. So that was my assumption. The goal here is to first compare the two methods. You've probably seen Bayesian models already, so have a quick kind of conceptual discussion here. And then some practical implications that are based on those differences, especially things like submitting a journal with this type of method, what types of comments people may get, etc. And then a focus on running, inspecting, and visualizing models, specifically using the RMS. There are different ways to run Bayesian models in R and in Python, same thing. VRMS is just probably the most widely used method at this point, unless you are in statistics and you really want to fully customize a model, you're good with VRMS. Even with VRMS, there's a lot of customization that we can have. Some other packages too, but especially packages for visualizing. And the reason why I'll focus on the visualization as well is because everything in a Bayesian model is a distribution. And so visualization is just something that we have a lot more things we can do visualizing these types of models. Now, because this is just an hour and 10, 15 minutes, and then you can stop me at any time. And I think it's best, unless you prefer to leave questions to the end, but just feel free to stop me. We won't have time to go into certain aspects that are very interesting. For example, the discussion of priors. We'll talk about priors, but we won't compare different types of priors and all that in the actual models. A model comparison to using information criteria or things like cross-validation and all of that. This is tied to a separate discussion, which is what do we use statistical models for in linguistics, right? Do we use them for to predict new data, or do we use these models to infer certain patterns from the data? And these are totally two completely different things, right? So when we are comparing models based on information criteria, the better model is not necessarily better depending on what we're doing. It's just, it could be better from the perspective of just purely statistically speaking. You just have fewer variables, and those variables do a better job predicting new data. But if you're actually trying to infer certain patterns and use a specific framework, representational assumptions, and all of that, it may not actually be the better model. Right? There's a long discussion about this in one of the references that I'll give you later. This book, which is, in my opinion, is probably the best book on stats I've read, which is Statistical Rethinking by Richard McEwith. It's entirely Bayesian, but it's not really a book about Bayesian statistics. It's also very kind of philosophical about what we do in stats and all that. And so we won't have time to go into those details or multiple types of distributions, which is a plus also that we'll see. And sensitivity analysis, which is super useful, especially to counter some typical criticisms like, oh, you're biasing the analysis. Yeah, but you can compare a range of possibilities. So we'll talk a little bit about that, but not much. Okay, so the basics here is really kind of the conceptual aspect, which is how we understand probabilities. There's a reason why the models that we normally use are called frequentists, so the statistical school of thought. That's frequentist, and that's because it's mostly based on the frequency of events, right? So we rely on large samples and the frequency at which something is happening, and that gives us kind of the building blocks of this type of thinking process. So that's why we call it frequentist. And the question we address primarily is what's the probability of the data given a parameter, which is our p-value. Right? Now, of course, in the past, people used to be super focused on the p-value, like old statistics kind of way, and nothing else. Now we see that this has changed considerably. We see a lot of emphasis on the estimates and confidence intervals and all that, right? Much more comprehensive interpretation of the results and not something like if it's 0.06, then the study is useless, and if it's 0.049, it's perfect, I'll get it published, and that's it, right? So going back to the null hypothesis significance testing idea. Now, if we move that to a Bayesian perspective, we now start with an assumption that is not based on frequency. Like we can just start with an assumption, which is extremely important in situations where it's the first time that something's happening. Like, how do you consider past frequency if it has never happened before? And that's part of the reason it's a very useful type of method to, for example, during the war, to locate submarines and to locate the crash site of an airplane in the ocean. For example, is a famous case of the Air France flight from Brazil to France in 2000 and something, I can't remember the year. They took a lot of time to find it, and they were not successful. And then they used a series of Bayesian models using priors as the locations that were more likely given what they had just done in their search, and they very quickly located the crash site. So this type of situation where it hasn't happened before, so the notion of frequency is just very abstract and unrealistic. So this is kind of conceptually one advantage. And more technically, but also kind of addressing the whole hypothesis testing part of it, is that we're asking the question, what's the probability of a parameter given the data? So exactly the opposite of what we have in the frequentist model. Now, most of the time, in simple applications, the result will be very similar. And that's part of the reason why after you go through all the hassle sometimes of running a Bayesian model and you get to your estimates and you think, okay, these are very similar to the estimates I had before. What's the point, right? So, and there are different reasons for that, which we'll talk about today. So this is really the P of a parameter given the data, which is most of the time what we want to know. We don't really want to know the probability of the data. We want to know the probability of a given hypothesis a lot of the times. It's just more, intuitively, it's more relevant. And every time you read about Bayesian models, there's usually this textbook example that uses a test for a disease. It's always that. It's like 99% of the time. So let's start with that, and then we move to more realistic scenarios. So this is Bayes' rule. Probability of a parameter given the data is equal to the probability of the inverse of that, the probability of the data given the parameter times the prior. So this part here is a major component in any Bayesian model, which is what I mentioned before about the search for an airplane. Like, where have we searched before? Can we incorporate that experience into the model to reduce the probability that the crash site is in those places that we've been to already? Right? And then we divide that by the probability of the data, which is just the marginal probability. Now, for this example, which is a very simplistic example, so we can actually calculate it manually, it works out. In realistic applications, we can't really calculate things this easily. So just defining our values here, the probability of the disease, we're given a situation here. We take a test. I am randomly selected in the population to take a test for a disease, say COVID or something, right? And the test is 95% accurate in positive results, so true positives. But we know that the disease is pretty rare, so 0.1% only. This is a piece of information that's often ignored, but it's clearly very important. And we want to know what's the probability that my positive, so I take the test, I get a positive, do I have the disease? What's the probability that I actually have it? And this is one of those situations where the answer to the question is counterintuitive to 99% of the population. Because most people would say, oh, it's probably very high. It's like 90% probability that I have the disease, right? Now we just have to define the values here. We know that the probability of the disease is 1/1,000, so it's not a common disease. Probability of not having is the complement of that. Here's the accuracy of the test, and here's the complement of the accuracy. So we have to consider the two possibilities, only two possibilities in this case, because it's a binary scenario for the marginal likelihood of the data as a denominator. Now, once we have those values, which they're all given to us in the context, but the conclusion is that the probability is less than 2%, right? And this is counterintuitive to most people. even after looking at the calculation, you probably continue to find it a little counterintuitive. Like you wouldn't say it's 2%. Like if it's you, it happened to you in real life, you would probably be more afraid than 2%. I would, I don't know. It's just, it's an intuition that doesn't completely process my brain. Now the question here is, okay, what happens if I take the test again and I get another positive? So I'm kind of pushing my luck there just to make sure that this isn't a false positive, because after all, it's only 2% probability that I have the disease. So I take it again. So the idea here, the intuition behind the whole process is that we can always update our prior belief about something given what we just did. Right? So now the prior probability of having the disease is no longer 1/1,000. It's 2/100, right? Because that's the updated value, or less than 2, but roughly 2. So if we do the second test, we end up with a different calculation. We just have to update our priors, and the result now is 25%-ish. Right? So now the probability is a lot higher. It's still much lower than what people would probably guess in the first test, but it's 25%, which is not super low. Right? It's a considerable probability now, and we can keep going, right? So you can keep updating the prior and all that. Now, what a traditional model would do in the second time that I do it is the second test would not consider it that I just tested positive. That's just unknown information. It's completely ignored. So the fact that if I tested positive 10 times in a row and I'm testing again, just to be sure, a frequentist model would just treat it as the first time, which is completely counterintuitive. But why would you treat it as the first time? We know there's a high chance that you have it. So this is kind of the intuition of why priors are so important, because we rarely start a study with zero knowledge on the topic. Like it's very rare, not recommended. So the prior here plays a crucial role, makes all the difference. We can change our conclusions based on it. Here we multiply the result by roughly, 12 when we update our prior beliefs. So it goes without saying, and this is kind of a nice characteristic of this discussion, or the relationship here, is that the stronger the prior, the harder it is to change the posterior, which is our conclusion. Now this makes perfect sense if we think about cognitive dissonance and all of that. Like if we're really set on something, it doesn't really matter if we see data showing us otherwise, the posterior will not change too much. So here's an example of a situation where we read some studies on a particular parameter, and the studies agree that the value of the parameter is more or less 0.2, something like that. So that's what we see in the literature. Now we run an experiment, and in our experiment, we found about, let's say, 0.6. So there's a good deviation from my study and what I see in the literature. So in a kind of standard scenario, my conclusion should be, depending on how strong the literature is and on how well designed my experiment is, the question is which one should value more, right? Assuming that they are equally important, which is rarely the case, right? Quantitatively speaking, then the posterior will be a compromise between the two. So a frequentist model would just say your conclusion is based on your data, and that's it. So the posterior, which we don't use that, but the parameter that I would arrive at in a frequentist model would be identical to the data that I observed, because that's just what I did, right? Now we know it's not like that. So the researcher is there exactly to avoid this type of simplistic conclusion, but that's what the model is doing. It's just ignoring completely what the literature has done so far. Now we can see this visually here. If we play around with priors and posteriors. So let me give you one example. Here's the situation we just saw. So in blue we see, can you see the colors there?
Yeah.
Good. And so the blue one is the conclusion, the red-ish one is what I know before collecting my data, and then in gray we see my data, right? So if the literature is saying that the parameter is 0.5, for example, I collect some data which is now 0.7, let's say the parameter conclusion is it's halfway there. Now, if I collected, this is 0.5, of course, is the observed data, the conclusion, sorry. So here I collected 30 data points, 20 positives and 10 negatives. So it's 2 to 1, right? Now, if I made this 40 data points with 20 positives and 20 negatives, we would be agreeing with the literature that says that the parameter is 0.5. It's like a coin toss, right? So the literature says the coin toss is 50% probability. I just confirmed that, so everything is aligned. But if I collected 120 points, 100 of which were positive and only 20 of which were negative, now the posterior is much closer to what I observed than to what the literature says. Now we can, of course, multiply the sample size, and as we do that, our conclusion will be more and more similar to what we observe in our data, because it's just so much evidence against what has been said before that the posterior just can't do anything but to move towards our data. So that's kind of the intuition behind it. And it's the intuition behind any model, even models that are much more realistic than this, right? So the idea here is very simple but powerful at the same time, which is you should always incorporate what you already know given in a given phenomenon into the model. Now, conceptually, this is all fine and good, and sure, we all agree. In real life, in a study, this is more complicated because it involves some, almost like a meta-analysis in order to arrive at a prior that's well adjusted and informed. So that's kind of almost a separate study in and of itself, which it's a lot of work. Right? So now, in real life scenarios, we can't just calculate analytically the Bayes rule. As you've probably seen examples already on this. So if we only had 7 variables in our model and we wanted to consider, of course, now we're talking about parameter values that are continuous, right? So if we wanted to consider 1,000 values only for the 7 variables, we already end up with an amount of calculation that's just not doable, even by a good computer. Right? So that's why we never actually calculate these things. What the model will do is it will just sample from the posterior distribution instead of actually calculating the posterior analytically. And there are different methods to do this sampling. That's kind of the center of the analysis here, is which algorithm we use to extract this. You can see the footnote there because I have something on top of it. All right, so there are many options. There are very simple models, like one of the first ones, like the Metropolis Hastings algorithm. There's JAGS, which is so there's the Gibbs sampler, and then JAGS means just another Gibbs sampler. And then there's STAN, which is the state-of-the-art algorithm used these days that has been developed by a bunch of people, including Andrew Gelman and colleagues. So these you may have heard about these algorithms. It's basically like a random walk. That's the metaphor that's used, except that for STAN, the better analogy would be it's like a random travel of a ball in a concave area, just because it uses Hamiltonian Monte Carlo. Now it's Markov chain Monte Carlo, Markov chain because the current step only depends on the previous one, not 2 steps ago. So we always consider the next potential value based on the current one. We don't care about the previous ones. And Monte Carlo because there's some random aspect to it. So in a very simple scenario, the algorithm works like this. Of course, this is a very simplistic illustration of the process. STAN is extremely convoluted. But for our intents and purposes, this is what we have. So we start picking a value for a parameter, a value for our beta, for example, for our intercept. So I'll try to contextualize everything here in terms of regression models, because that's the examples, the example that I'll use later. So you pick a value for the intercept, any value that's reasonable. Then you calculate the probability of that value given the data we just collected. That's it, step 2. Then we propose a new value to calculate, to sample from, right? And we calculate the probability of that value. So now we have 2 probabilities, value A and value B. Now, if the probability of value B is higher, then we just definitely move to that location in the parameter space. If it's not higher, then there's a calculation, which is just one example is, okay, just divide both probabilities and move to the new place as a function of that probability. So it's not a categorical jump. So you have to decide whether to accept this proposal. So this is where the algorithm comes into play. Different algorithms will have different proposal strategies. And once we repeat steps 1 through 4 many times, it just so happens that in this space of parameter values, the parameters that are more likely will be visited more often. So we end up with this cluster in a particular region, right? And that's why we can visualize Bayesian models in that way too. Simply because everything here is a distribution, unlike frequentist models where we have access to, at least at the end of the process, we have access to a single point estimate. So one question is, how do we know that this is accurate? How do we know that we have converged? And we usually use multiple chains, right? So you may have seen or heard of the chain. So if we use only one chain, we wouldn't be able to tell if there's a cluster of that chain in a particular area, if that chain is correct. It could be wrong. But if you have multiple chains and they all cluster in the same location, that's a pretty good indication that we're right. So this would be, we're searching for the values of a given parameter, say a beta hat here. And we all cluster around this area. We can see that all chains are kind of together. We can't tell them apart. This is usually a good indication that this has converged, as opposed to something like this, right? So if we have 4 chains that starts, and they always start separately, they will start at different points in this area, and they will tend to converge, but here they haven't. Now in the dashed line represents the true value of the simulated data. So only one chain here is actually in the right place. And of course we would know that because we never know what the true value is. But maybe if we just left the model sample for a longer time, we would be able to arrive at a cluster where you have convergence, right? That's a kind of an advantage of these models, because if you let them just do their thing for a long period of time, chances are that they will converge eventually. So this is just something to consider as another kind of advantage. So here's just one picture that if you look at this picture, you already know in terms of diagnostics that the model isn't good. It's not working as it should. So trace plots, good visual way of seeing the diagnostics or talking about diagnostics in these types of models. Now the problem is, of course, we are always looking at joint distribution. So if we have a model with a very simple model, a single predictor, so we're looking at the posterior distribution of beta 1, but we also have an intercept. So we already have this joint distribution of 2 parameter values. This is already complicated, right? If you think about the manually, analytically, it's very complicated. Now imagine a model with 10 main effects and then by speaker random slopes and all that. It's just a ridiculously huge combination of parameters. And of course, we wouldn't be able to visualize that for obvious reasons, but just to give you a sense here of a cluster of 2 posterior distributions in a particular location. Right? So this is what we can visualize for every pair of parameters in a particular plot, just to make sure that they are clustering correctly. So everything is a distribution. Now, here's what happens if this is something we will not do, fortunately. This is what a simple model using STAN, which is the language that was developed to run Bayesian models using Hamiltonian Monte Carlo. This is a separate language that just defines models, right? And it works like this. I don't know if you can see that. We can define the variables in the data, we define the parameters, and then we define the model with the priors at the end. So there's a whole syntax involved. Part of it is familiar. Maybe the last line is familiar because it uses the squiggle. And you can see normal, so it's saying, okay, the response variable is normally distributed as a function of a regression model. But for complicated models, this is very convoluted. Like we would spend a lot of time figuring this out. So fortunately, BRMS basically translates the syntax we already use into this. And we can see the result if we save the model and open it up later. As there is an example there. All right, so I'll use tidyverse, of course, and some other packages. I think base plot is not necessary here, but it's just because BRMS already includes a lot of the functions from that package. Have you used BRMS already? Maybe? Some of you, yes? Okay. So this is the data, and all the data, there's a link that you can download it from, so I'll give you the link shortly. So it's just from language R, the package. So this is a subset of Bayesian study on Danish, where you have multiple suffixes and reaction times and all that. And this is a subset with 5 suffixes. Now, the reason why I chose this is because I don't know if you've come to this situation, but back in the day, some time ago, right, people used to run a specific type of regression with multiple comparisons, like ANOVAs plus Tukey or something like that, right? And that was, of course, it was much more limited, but there's an advantage in the output that a lot of people still want at times. Because when you run a regression model, it's always the case that you have to compare all the levels of a factor with a single level. And sometimes that's fine, because that single level makes sense as the reference. But here we have 5 suffixes, and maybe there is no plausible reason to assume that one should be the reference, right? So we might want to, okay, there are ways to solve the issue. We could just run one regression model with a single reference level every time. That's, of course, something that people who are into p-values don't like, because you have to correct p-values for multiple comparisons. That's why we do the, for example, Tukey HSD after the ANOVA, right? So the p-values are inflated to avoid type 1 error. There's multiple comparisons. There's a multi-comp package that can be used. But sometimes it's a little annoying because you just want to see all the comparisons. And that's something that is sometimes used because you don't have a good reason to use a single suffix or affix as your reference point. So that's why I chose this data set, because I'll show you how it's very easy to customly design whatever comparisons we want. And because we don't have p-values, we don't have to worry about inflating p-values, like that. So that's one important difference that can make our lives easier. So this is what the data looks like. We have 5 affixes. You can see the box plots and the means there in orange. I don't know if you can see the orange. It's tiny. It's big enough on the website, but so this is just to show, okay, that they are ordered, but I don't know, is there a reason to pick one? So we know here that R is going to use var as the intercept, because it's always alphabetical, which is very rarely the level that we want. Right? It'd be an amazing coincidence. So this is just a typical regression model using LM, just to use this as a comparison. So we can see how this is going to be understood by the model. We have 5 suffixes, so we have 4 or j minus 1 slopes, which means we're looking for 4 slopes and 1 intercept. You can see the table with results here. So we can see that there are 3 affixes that are statistically different from var. Now, if we wanted to know, okay, but I want to know if A-day and N-day are different. So we'd need to run another, we'd have a couple of options. We could run the multi-comp on top of the model, or we could just run another regression changing the reference level, which I think is what a lot of people do. It's just quicker to re-level the factor and all that. Now, if we do want to report multiple comparisons, that's a problem, because there's always a reviewer who will say, yeah, but wait a second, you're just running multiple comparisons and using the same p-values, and that doesn't work like that. So here's the figure from the model. We can see it's not a very useful figure, but I'll use this figure as an example to compare it with the figures we'll do later for the Bayesian model. Now, the advantage of this type of figure is that it's very quick. You may have used already the sjplot package. The good side is it's very easy because you don't have to manually plot things, but of course it will do its thing, right? So if we want to change certain aspects of the figure, it's using ggplot, so we can just attach different layers to it, but it's not that easy to change everything. So if you like to customize your figures, not here. Okay, so this is what people used to do. So because we're doing a simple model, we are essentially running an ANOVA anyway, right? So we run the ANOVA and then we run the post hoc, a post hoc test like 2KHST, and we end up with all the multiple comparisons, and the p-value is adjusted. So we can see here that 1, 2, 3, 4, 5 of the 10 comparisons would be rolled out as non-significant, just because the p-value has to be inflated, or the threshold is. So 5 out of 10, so half of the comparisons have no statistical significance. And of course, we're only looking at we're not including by participant effects, right? So it's very simplistic analysis. But even here, half of the comparisons have to be done. Now, it's funny that in the literature, when we see something like 0.0503 or 0.06, we always say that it's approaching significance. It's moving in the direction that I want it to move. It's never running away from significance, which it could be, right? So here's the figure for the multiple comparisons. I find it easier to see this type of thing. So we can see that there are essentially 5, if we're strict with the arbitrariness of a p-value, there are 5 comparisons that touch or include 0 in their interval, in their confidence interval. All right, so this is the equivalent model using BRM. I'm saving the model. So I don't know if you've done this when you use BRM, if you save the model as a stand file to look at it later, because it gives you a sense of what the actual structure is, and it's depending on the model, it's a pretty scary file because it's ridiculously long, and you just really thank BRMS for existing after looking at that file. But it gives you a sense of how to set it up and how to set priors as well. Of course, you can set priors within the function or before as a variable. It's pretty easy. And it's very useful to, I mean, I always do this. I don't know if you are in the habit of using our data files or extension. So saving the model is important because, as we all know, these models take much longer to run. Even a simple model like this will take maybe a minute, which is a lot compared to the frequentist version, which just runs immediately, right? So if it's a convoluted model, it could take, I don't know, 20 minutes, right? So you definitely want to save this fit, and this fit is also available, so you don't have to run the model to run the figures later. So it's a good idea to save both the output and also the compiled stand model. Now, using multiple cores is essential, right, to speed it up. So if you're using, I don't know, if you're using 8 chains, you could use 8 cores, 1 core per chain. And this is the output. So we don't need to use summary as if you use the BRMS, you know that you can just hit fit whatever name you give it, and you get the result here. Of course, the most important part is population level effects. It's very similar to the model we ran before, right? So if you compare the estimates, they're very similar. You would probably think, why would I do this much work? I mean, it's not a lot of work, but if it's very similar. So we'll see the differences later. We normally look at R hat as our diagnostics, R hat and the effective sample size. So the R hat should be 1, right? So if it's 1, it's good. There's a whole explanation for why it should be 1. Doesn't matter right now. The effective sample size, of course, is how many of the samples that we're taking are actually useful, right? Because we're taking 4,000 samples here. That's the default. We can change all of that. If the model is having some hard time converging, we can just have more samples, right? 10,000 samples. Now, if we have 4,000 samples because we have 2,000 samples per chain, but we are using 1,000 samples just as a warm-up because it takes some time for the walk to arrive at the cluster where the values are more likely. So this is 1,000 per chain, 1,000 times 4, that's why we have 4,000. Of those 4,000, there's a lot of autocorrelation between certain steps. So there's a lot of times that you get stuck in certain areas because a particular point is correlated with a previous point. So you have to get rid of those because they're less informative. The more correlation there is between the points, the less information you can extract from it. So that's why effective sample size is a subset of 4,000. So there isn't really a rule of thumb of how much is good enough, but here we have over 50% of the draws are effective. So it's good enough, so over 2,000.
Would you say there is a rule of thumb about how many warm-ups to include? How many chains, how many warm-ups?
It depends on the complexity of the model. So for this model, we could have 500 as the warm-up, that it would be totally fine because it's a very simple model. But if it's a more complicated model with interaction terms as random effects, for example, that would be good to have more warm-up. So
it strikes me as something that varies a lot in literature. This is why I ask. I'm just wondering, like, when you do these models, like, you must have some sort of rule of thumb in mind for how complex the model needs to be to warrant.
That's true. It also depends on the priors, right? Because we can help the model not get into areas of the parameter space that make no sense. That's why even when we don't have a good idea of what to expect, we shouldn't use non-informative priors, right? Because we know that certain values are just impossible. So if we're looking at the case here, we know that the slopes cannot be 1,000. That's just unrealistic. This is log reaction time. It will not be 1,000 log milliseconds. So we could just center it around 0 and have some standard deviation, and that would speed up the process too. So having good priors will also help us with the problem of how much warm-up do we need until we get to the point where this is reliable. But it really depends on the model, on how complicated it is. It depends on whether we're setting the seed to use roughly the same starting points to, it varies a lot. So every time we run it, it will be slightly different, of course, because we're randomly sampling. But it's randomly different. It's slightly different, but it will virtually be the same, of course. It's just, yeah, it kind of gets, so it's very common to have bulk ESS of 300 if the model is complex enough for certain terms, especially, so here we have sigma. So sigma is also estimated as the standard deviation, right? Which it isn't in a frequentist model. So that's actually a pretty nice characteristic of these models, because you no longer have to assume that all the groups have the same variance, which you have to, I mean, here we're not playing with that, but you could estimate sigma for different terms, which is really nice. By default, it doesn't, but it's just something to bear in mind that heteroscedasticity is really not an issue if you just have to customize it enough to estimate that. Now, in the data, variance is pretty similar across the board, so we wouldn't have that problem here, but it's very common to have that problem, right? It's like one group, it's all over the place, and the other is really consistent. Yeah. Where were we? Here. All right. So here's the easiest way to plot it is just use the plot function. It gives us the posterior distributions of the model and the trace plots. And we can see the trace plots look fine. If we can't make anything out of it, it looks fine, right? If it's all on top of each other, it's fine. Yeah, or caterpillar plots. So the model converges well, so you can see it's all over. At the end of the 1,000 sampling, all of the chains are together, clustered, etc. Now we can get a little more specific. with a function called MCMC plot. Maybe you've used it, right? So the default, I think, is this, which is the point with, I think it's 50% highest density interval and then 90% or 95 or so. We can always change that. Now this, here I'm using this very nice possibility of selecting certain variables, because the thing is, especially when we're running a model that has random effects, which we'll do later, there's just so many variables. There's a random slope by participant, there will be so many variables. And here I just want to plot the population level effects. Now it just so happens that the population level effects all start with B underscore. So you can just use regular expressions to select just that. So I don't want to see sigma in the figure. Most of the time we don't. But so this is kind of similar to the figure from before. We don't see the intercept because in this type of model, everything is a difference relative to bar anyway. So it makes perfect sense to just plot the other four here. You can get a little more specific by looking at the distribution. Now this figure here resembles a figure from a frequentist model. But of course, in a frequentist model, this is not a distribution. Whereas here, it is a distribution. So that's why this type of figure is kind of nice, because it really denotes that, okay, we're talking about a distribution of values. So values that are closer to the mean are more likely given the data. It's very intuitive. It's kind of, it's counterintuitive that a method that is computationally harder is much easier to interpret. Because take confidence intervals, which is something that a lot of people misinterpret. A lot of people interpret confidence intervals the way they should interpret credible intervals in a Bayesian model. So values that are inside and closer to the center are just more likely. It's just so much easier than what confidence intervals really are. Just something, it's like p-values also. All right, so this is a typical figure that would be the model, right? The model is actually the distribution, so this would be enough to report the results of the model. Of course, it doesn't talk about diagnostics, but still. Now, the thing is, because these models are not all over the place, depending on the field, right? So in cognitive science, we were talking about this before, if you are in a subfield that doesn't do this very often, you have to be aware that reviewers may not like this, right? Because it's too minimalistic. So first, where are the p-values, right? So there's some explaining to do, and a lot of people are not comfortable with not seeing p-values too. So depending on, it's area specific. It's also, if you come from a time where you saw p-values, it will be difficult to not see them. So it's just something to bear in mind, that you may have pushback even before you consider priors. When you consider priors, then there's a whole other discussion, which is, but if you're given the models on priors, you're biasing the model. That's a very common criticism. So this is a more realistic situation though. So we just saw a simple example with a simple model that has no random effects at all. So this is the same situation, but now I'm using lines to represent averages by participant. And you can see it's a little, there's some variation as expected, right? They're a little bit all over the place within the boxes, kind of. I've ever tried playing around with the actual values from the posterior. And the reason why we would want to do that, is that it gives us all the control to make any comparisons we want. So if everything is a distribution, we can subtract distributions from distributions, and we end up with the distribution that represents the comparison. So we can do whatever we want with the posterior distribution. So it's a little more manual, but at the same time, it gives us all the control that we want to extract our samples. So we can use this function. I don't know if you can see it, because for me, it's very small looking from where I am, but we can use the asDrawsDF function, and that will just extract all the 4,000-ish, well, exactly 4,000 draws and transform it into a data frame. So it gives us already something that we're familiar with. Then I'm transforming it into a table here And from there, we can select and rename all the variables and all that. So here, for example, I am selecting the variable b-intercept, which I know represents bar. And I'm just renaming it as bar because that will be much easier to work with later on. So I'm just using an asterisk to remind myself later on, okay, this used to be the intercept, just in case, right? And so once I rename all of this, I can just do all sorts of things with this. I can manually create a figure that looks like this, for example. Now, this looks like the figure from before, but it has some advantages. So first, because it's a figure that we are creating ourselves, we can manipulate it however we like. For example, we can add some observations at the right-hand side that address sometimes we have some questions from reviewers that are like, okay, I can see the distribution, but where is the point estimate? Where is the estimate? So some people don't like seeing distributions and they like to see numbers too. So we can automatically extract the means of each distribution on the right-hand side here and the credible interval as well, because that's the other thing, right? The shaded area in the middle of the figure, so the dotted line represents 0, which is useful to visually see where in the distribution 0 is. So in a traditional frequentist model, you would say, okay, if the line crosses the interval, then the p-value is above 5, which means it's not significant. We should just ignore that result or something like that. So in a very categorical approach, here it's just saying where in the distribution 0 is. So basically, if 0 is in the middle of the distribution, it means it's a very likely value given the data. So it's kind of saying, okay, it's not a credible effect because, right? The shaded area represents the rope, which is the region of practical equivalence that I think I mentioned this on Friday. So if the entire distribution is inside the shaded area, that would be essentially like accepting the null hypothesis, which is something we can't do. It would be like saying, okay, this is a null effect, objectively a null effect, because it's practically equivalent to 0 in terms of its distribution. Now, of course, it's not the situation that we have here, because maybe area here is, I don't know, 50% within the row, but we already know that 0 is a quite possible value, so we wouldn't conclude that this is statistically credible in a way. So
what was the other name that you used for the rope?
The region of practical equivalence, yeah. I've never tested this with reviewers in linguistics. It is something that exists in psychology, but I have my doubts that if you ended up with a distribution that's entirely in that region, and you said in the paper, because this thing exists, we can now say that this is actually a null effect. I have my doubts that people would say, oh yeah, that makes perfect sense. I think there would be some pushback. If you're getting reviewers who are like strong frequentists, there would be like a whole debate, I think. So it's always a possibility. It really depends on the journal to what type of reviewer and the background of the reviewer would be. But it's just something that it exists and it is used. So it's kind of useful to. It's also intuitive that this would be a thing, right? Because if you actually have a distribution that is clustered around 0 and is really narrow, that means the model is really certain that that's where the values are. And if it's around 0, the fact that in a typical model you cannot say, yeah, there's nothing here. You have to say, oh, I wasn't able to reject the null. Like there's this whole culture of phrasing things correctly because it's true, right? But at the same time, it's in practical terms. It's, yeah, sure. So this allows us to be a little more, like the connection between what it is and what it is in practice is more, I don't know, aligned than in frequentist model. Now, the nice thing about this, once we extract posterior distributions manually, is that we can now compare whatever we want, however we want, right? So I can take this posterior table and I can just create some columns. So I'll just create a column that compares these two suffixes here, 80 and end. And what is that comparison? Well, I just have to take the intercept and add the slope to get the true absolute value for that affix. And then I subtract from that the same thing from another affix. So I can just do these things. So in this particular case, because I want the absolute values, I'm using the intercept every single time. And after that, I can just rename a couple of things. We know that the comparisons with bar were already there, right? Because all the slopes were already comparisons with bar. So we just have to add the other ones and then change the existing names just to keep things consistent. And then once we do that and transform the table, we can easily create a figure like this one, where it might be too small, but where you can see all the 10 comparisons. And there's no need to adjust anything because p-values are just not a thing, right? So we don't have to adjust for multiple comparisons. We're just comparing posterior distributions. And here we can see that if we want to use a categorical threshold, if we want to say, for example, I will only accept an effect if 0 is not inside the credible interval, which is kind of transporting the frequentist mindset onto here, then in that scenario, only 2 comparisons would not be statistically credible, right? Compared to 5 when you use the ANOVA, right? And of course, this makes sense because in the ANOVA scenario or in the linear regression using frequentist method, we have to adjust for multiple comparisons. So it's a price we have to pay, right? Otherwise, people will, it's just not going to go through, right? If we don't adjust, there will be pushback.
But there's a reason behind, it's not just a random thing that post hoc that p-value adjustments were introduced, right? The idea is that like if you're doing a bunch of comparisons, the probability increases that you may just have a spurious finding in there, and so this is supposed to correct for this to some extent. Can you talk about how that relates to this type of modeling? Is this still a concern that we need to have? Or does modeling things in this way sort of get rid of that possibility?
So it is true that there is a rationale, and part of the rationale is because of the numbers that are set from the get-go. So if we're using a 5% threshold as acceptable for a particular type of error, and so type 1 error, then you can calculate how much of that will increase after multiple comparisons and all that. But a lot of that is kind of tied to the notion that of null hypothesis significance testing. So in this kind of scenario, you don't see people making adjustments like this because there is no goal to reject a hypothesis here. So that's kind of part of the difference. But it is true that if we're making more comparisons, intuitively, we would need to make some adjustment. So one option, for example, and we'll see the next example, the moment we add, in this particular model, the moment we add random effects, that will kind of be incorporated in the model because all the posterior distributions will be wider because of the error term. But in and of itself it's not something that people in this framework will debate over.
Yeah,
which doesn't feel right.
Difference. I totally get the conceptual difference.
Yeah.
But I think in practice,
I can see a lot of pushback.
What you are trying to do is to reject the hypothesis, right? Any paper that you're writing, you're trying to either support or not a particular hypothesis. So
right, a particular hypothesis. But I think that's the main advantage, because you can use Bayesian base factors too, which is something that people use to approximate the two worlds a little bit. But I can totally see that point that I've never done this in a paper, multiple comparisons, but I can totally see a lot of pushback saying, yeah, but how do you adjust for multiple comparisons? And the fact that it's not a standard to do this, you can make certain adjustments, For example, you could include error terms for every time you make a comparison to increase the width of the posterior distribution, even without random effects. So you could do that, but you don't have to do that. And that is a little uncomfortable in a way, because if we come from frequentist analysis, and I do too, right? So it just doesn't feel like you will be able to get away with this. That's my impression. But again, it really depends. It's like the discussion on priors, like how, if adding priors informs the model based on a certain particular pattern that you're interested in, how is that not biasing the model? Like what is the line dividing biasing the model and informing the model? And there's a nice paper by Andrew Gelman on that. I think it's 2008 on common criticisms related to Bayesian analyses. But I don't see this as a replacement of, some people do. So some people are like, oh no, yeah, this is the thing, and I'll just do this until I die or something. I think it's a healthier way of looking at this, is to think of this as a complement to a traditional method. That's kind of
a frequentist method.
Yeah. It's like you don't have to do one or the other. I mean, what I do normally is I start with frequentist models because they're just faster, just to kind of explore the data. And once I have a sense of where I'm going, or if I hit a wall because the model is too complicated, it doesn't converge, then I'll move on to the next part, which is this, where I can customize the model a little better. But for multiple comparisons, technically, yes, you could do this. The question is whether in practice, reviewers will see this and be okay with it. That's a very different question. And I don't know the answer to that, because in my experience, like the reason why those numbers are on the right-hand side is because a reviewer has asked me on multiple occasions. I've had this being asked, which technically doesn't make much sense, because if you see the distribution and you see where 0 is, the actual value is there, right? The whole distribution is there. But yeah, I can see why. Yeah, sure. I just want to see the main. If you order the posterior distribution, like they are ordered here in terms of which one is more positive. But yeah, it feels like you're getting away with something.
Well, only to the extent that the language around how we frame our research is more in line with the frequentist approach, right? I mean, what Bayesian modeling really begs us to do is to just view our data in a fundamentally different way and talk about it in a fundamentally different way. But the reality is that it hasn't evolved that much. So you're sort of left with this mismatch between setting up your hypotheses in a very much frequentist sort of based perspective, but then interpreting the data relative to the Bayesian model, and there's always going to be that kind of. That's
true, because we're kind of built, the past decades were kind of built around the notion of rejecting a null hypothesis.
Right.
And it's very difficult to detach yourself from that. And then there's this asymmetry, as you mentioned, like we're using a method that doesn't care about that, but the minds of the kind of the framework still does to some extent. What the advantage of ignoring the null hypothesis is that you can actually test your hypothesis, right? You can check the probability of your hypothesis being reasonable or not, as opposed to just rejecting the null. But yeah, I totally get that.
Reasonable. What does it mean to be reasonable? So at a certain point.
Yeah, but that is, in a way, that's one of the reasons why I think people in math tend to look down on stats, is exactly this type of subjectivity, right? It's always been there, even with rejection of null hypotheses, and like the fact that if you intended to compare, let's say, and actually use these same affixes as an example for another discussion, which is if I start the analysis by saying, okay, I want to compare these two suffixes, these two specific suffixes, and I subset the data and I only look at those two, they're significantly different. Fine, I publish the paper. If, however, I start with 5 suffixes and I do multiple comparisons, but at the end I'll just focus on those 2, they're not significantly different because of the multiple comparisons, right? So basically, this is saying that my intention at the beginning, the data hasn't changed, right? But my intention changes the results, quite literally. Because if I intended to only look at those 2 and I never looked at the other 3, removing them from the data or just running the ANOVA on those two, I would get a statistically different result. And that's kind of the other side of the multiple comparison debate, which is sometimes it gives you this weird scenario where the intention of the researcher dictates the result that you arrive at, which is super philosophically bizarre, right? Counterintuitive. And the same thing for when you stop collecting data, that sort of thing.
Yeah.
There's a nice discussion by Krushke on this, how, of course, Krushke will defend Bayesian analysis no matter what. Like he's as Bayesian as you can get. I'm much more of an agnostic on this topic, but so here's the other model, the random effects model, and exactly the same thing as we would do with the frequentist linear regression. This is the nice thing about VRMS. The nice thing here is that we can actually, one thing that normally happens is if we have an interaction term and we want to have a random slope for the interaction by a participant, for example, it's quite possible that the model will not converge because it's a very complex model classification. Whereas here you can just, if you have convergence issues, you can just add more iterations or change some of the distributions, adjust some priors. There's a lot of things that can be done that will either solve the problem or it will tell you more or less why you're having the problem because you'll be able to inspect the walk, right? The chains and all that. So you can see exactly if there's a point in the chain where things just fall apart or something like so. In that way, it's a little more transparent in how we can get into the diagnostics and visually inspect everything that's happening. So this is what happens if we run the same model. So on the left, we have the model from before. On the right, it's the same model, but now with a bi-participant random slope by affix. So I'm not plotting the random intercept by word, but we could too. Right? And we can see here that once we do this for one model, we can use this kind of the same code and just adapt it to a different model. So here is just exactly the same rope. The rope doesn't change because you have random random effects. So the posterior distributions are very different. They're much, much wider, which makes sense because we're now accounting for the variation that we have across participants. So now if we were using a cutoff point, which as an aside, doesn't make a lot of sense, right? If you're using a Bayesian posterior distribution and then you just use a very categorical cutoff point to say yes or no as the answer, then why bother using posterior distributions, right? You could just use frequentist models and use the p-value to say yes or no, right? But again,
the journal wants you to be modern.
Exactly,
these
exactly.
models.
But then the thing is, if you start to relativize too much, people will just say, okay, is there an effect or not? Like there will always be that question, especially from people coming from, which is everyone, from frequentist data analysis, right? So the more you try to say, look, the picture is a distribution and it has to be interpreted in a very kind of non-categorical way. That's the whole point. Because let's say 0 is in the credible interval. Let's say 0 is, you have to see where 0 is, because if 0 is at the tail of the distribution, sure, it's possible, but it's highly unlikely as a parameter value, right? So that shouldn't mean you should, okay, yeah, there's probably no effect here. So unlike confidence intervals, where it doesn't matter where 0 is in interval, if it's in interval, okay, you have to, it has to be very categorical in this binary decision. Whereas here, it should be the case that you look, okay, where is 0 in that distribution just to, but this requires a lot of, I don't know, understanding from reviewers too, right? Because depending on the reviewer, they'll say, oh no, but what is a good location for 0? Yeah. there's no good location for zero, right? I mean, it's a distribution. It's not like there's a flag there that says after this point you don't have any
I think you do have
fact
to think
anymore.
about the perspective of the journal editor too, though, right?
Sure.
They want to uphold a particular standard of the work that's getting published. So to some extent, they have to have some sort of standard that they're going to hold people to. And if they allow one researcher to get away with saying, yeah, it's far enough from zero that I think this effect is real, and another researcher not to say that this doesn't happen in other realms of
Sure.
reviewing, but there is a sort of practical consideration there. So I
There
guess
is.
what do you see as being the kind of next frontier in how we talk about these models so that it kind of makes the job of the reviewer manageable at the same time, allowing you to view the data with nuance in a way that sort of fits with the ethos of the model.
Yeah, and I think part of the problem is that depending on, okay, so people are doing this in different ways at this point, but part of the problem is this asymmetry that you mentioned before, where we use a model, but we package it in a way that's still kind of inherited from the previous type of, well, it's not previous because it's not like this is the continuation of frequency statistics. But for example, if I use Bayesian statistics and I'm trying to be very subtle and to add nuance to the results, but at the end of the day, I still say, yeah, this is good enough for me to say there is an effect. Well, that's a categorical conclusion based on a distribution that's by definition not categorical. If it's let's say clustered around zero here, you wouldn't have that categoricity in your conclusions, right? You can't. You can just say, okay, you can see in the distribution here that zero is a very probable parameter value, so it's just not clear enough, right? That's it. Now, it's not a comfortable type of situation to be in because what does that mean? It means no or yes, right? So, but
It means can't reject the null hypothesis.
Yeah, exactly. So, depending on exactly the shapes, that's why it's very difficult to actually have that scenario where the entire distribution is in the rope, because we can see it on the right here. If we add random effects, the width will increase, so it's even more difficult to squeeze it in. So it would be highly unlikely, but it could still happen depending on the sample size and how strong the effect is, how much variance we get. So I think there needs to be some sort of symmetry between the method and the packaging of the method and the results. And the whole discussion has to be contextualized in that way. And not just say, okay, zero isn't there, but it's in a position that I will conclude that there is an effect. I mean, that packaging doesn't follow from the framework. So, and I think it will take some time for that to happen because there's just this imbalance at this point of using a method, but still thinking like you're using a different kind of method. So it's not surprising that this will create some issues for reviewers and associate editors who will be called to arbitrate something. We have this reviewer that hates it and this one loves it. So what do we do now? So depending on the take and whatnot, right? So that's just something to consider. So one thing that can be reported to, which this is not the standard figure, by the way. I mean, this is just it's a figure that I like because it gives people the whole situation, right? You see the posterior, but you also see the single point estimate equivalent representing the mean of the distribution if the distribution is normal, which most of the time it will be in our applications. But one other thing that I like is to report, so this is the continuation of this workshop, is to add on the left, this is a gigantic figure. Let me see if I can reduce this. Okay, I don't know if you can see that, but you can see it well. But on the left-hand side, there's a percentage. And the percentage is just telling you how much of the distribution equivalence. So that it's more of a, instead of using a single criterion to say, yes, we found a result and versus no. Of course, if the distribution is far away from zero, there's no debate, right? But the interesting situation is when the distribution is around zero, but where zero doesn't occupy the center of the distribution. That's when there's debate, right? How far from the center of the distribution should zero be for me to say, yeah, there's some evidence here. And there's a bunch of things that we can use. Location of zero, first of all, but also how much of the distribution is inside the region of practical equivalence. So we can see here it's 40%, so clearly that's just a lot. A lot of the distribution, almost half of the distribution is in the region where you would almost be able to accept the equivalent to what a null hypothesis would be in this framework, right? So it's just several types of, or several pieces of information that we can use to give, okay, this is the complete picture, and discuss this, package this whole thing in a way that's not categorical when you cannot be categorical. Right? It's just, and that's the crucial difference, I think, between the two. Because in frequency statistics, you can always be categorical. You can just say, yeah, we fail to reject or we reject. It's always a binary decision, regardless of the. I mean, some people will go as far as to say incorrectly that if it's something if the p-value is super small, this shows that this is what's the phrase that people often use? It's much more significant, like comparisons of significance,
Yeah, right.
that sort of thing.
X size and significance or something like that.
Yeah. So all of that, of course, is problematic, but the conclusion is often not as clear as we want it to be. And I think that's a plus. The question is how you package that situation where the conclusion is not clear. If there's some evidence for a positive, so let's say here, the difference between bar and end is, so there's evidence for a positive difference, but it's not strong enough that we were able to reject the possibility that there's no effect, simply because zero is a relatively probable parameter value given the data, and because almost 20% of the distribution of probable parameter values lie within the region of practical equivalence. So we can use multiple dimensions in our reporting and packaging to give the necessary nuance and to kind of run away from a binary simple answer when one cannot be appropriately generated, right, or extracted from the model, which is often the case, especially in complicated models. It would be a little hard to get posterior distributions that are completely away from zero. So here, I think there is no distribution that actually has 0% in the row, which means sure that there are some differences between the affixes here, but they're not extremely different, clearly, which kind of explains why the R squared of the initial model was only, I think, 4% or 5%. Sure, there are differences, but there's a lot of variation, basically. And one thing that I added to this figure that I don't have in the figure from the slides is there are some circles there. And so the circles represent the offset of the random effect by participant on average. So basically each circle represents each participant. And so the distance between the circle and the center of the distribution is the average offset of that participant relative to that parameter. So this is also something that you can do if you extract the posterior samples instead of just using a function that creates. I think there is a function that's quick and easy that adds mixed effects. I think it comes from the base plot package, I'm not sure. But this allows you to really customize everything. Like you could add, for example, the by word random effect to the visualization, which could be very useful to give the nuance that we were talking about before. So this is kind of it. On the one hand, this complicates things, right? Because a lot of the times, okay, just give me the answer. It's like when you're teaching a topic that's a little more convoluted, and someone says, oh, okay, but what is it then, right? But the reality is that it isn't categorically clear sometimes what the effect is. And this is just translating that complexity into kind of the model's results. So this is this is what it looks like at the end. So the figure involves a lot of different steps, but it's it's easy to scale up, basically, because of the variables here are all just related to this part here. So this is creating just extracting the region of practical equivalence, the 2 points, and this is calculating the percentages within versus total. Basically. So it gives you this possibility to just add that piece of information. You could also overlay the two distributions, which can be useful to show how much of the posterior changes as you include the variance across participants. Now, this goes back to the discussion that Mercurius has in one of his chapters, in chapter 8, Statistical Rethinking. It's the red cover book, which is about predictive power versus inferential power. So do we want to, what do we want to do, right, with our data? Do we want to create the best possible model to predict other data, or do we want to create the best possible model to describe the data that we have? Right? Because these will give very different models. Like this is probably overfitting a lot of things, right? So it's possible that we're missing important distinctions because we are increasing the complexity of the model because we are afraid of making type 1 errors, which also need to be adapted to this framework. Since we're not rejecting or failing to reject type 1 errors, it's still the same thing conceptually, but it's just a little more subtle overall. So there are, of course, there are pros and cons, right? So we just talked about some of the cons, but it's also very time consuming to run the models, to decide which distributions to use. They're often unfamiliar to reviewers, for example. So when we talk about priors, there's always that debate. I talk about multiple comparisons, but I myself have never used multiple comparisons in the paper. I anticipate that it would be a little problematic, that someone at least would mention something like, wait a second, aren't you going to do something about this? Something like that. I suspect it would happen. And the thing is, if we're running models like the ones we saw here, without priors are there, they're mildly informed, we will get similar results for simple models. So there's always the question, okay, why am I doing this if the results are very similar? So if you're into the technical bits, sure, but for practical purposes, there's probably this argument that you should have a good reason to use the model. Right? Is it a complicated model that doesn't converge if you use the frequentist one? Sure, that's a great reason to use the Bayesian model, because the convergence will not be problematic most likely. Or because you want to compare priors, so you could do, let me use 2 priors representing 2 different theories. And then I can compare the 2 to see which model driven by which theory best explains the data that I have collected, right? So that's something that is kind of nice to do because it gives you a quantitative way of comparing theoretical assumptions that you wouldn't necessarily have with the frequentist model. And you could even compare different strengths of each. You could have 5 models for theory A and 5 models for theory B, making the priors increasingly more certain within each theory, just to see what would happen. So having some sort of sensitivity analysis that compares theories and that sort of thing.
So on the priors note, I know you're not going to tell us about how to decide about priors, but since it's a really big issue, are there any resources that you recommend?
Oh yeah, sure. So
specifically ones, if there are any that are oriented towards linguistics research. I found a lot of stuff that's kind of general cognitive science stuff, but not a lot that is kind of particular to.
Yeah, because that paper by Gelman talks about the typical criticisms about priors from people who don't like Bayesian models. So it's a good paper to have a sense of, okay, this is what to expect. Mm-hmm. Like people will ask you certain questions, right? And he has a pretty good, nice sequence of questions that are often asked of us.
Which paper is that?
It's Gelman 2008. It's Gelman 2008 criticism base or something. Yeah, this is it.
Okay.
Objections to Bayesian statistics. So this is the one. I have some code for sensitivity analysis comparing priors that is on OSF. So it's this chapter here. So it's comparing two theories. It's the theories in question are about language acquisition, but it could be any. It's the same idea. So I think I did something like 4 or 5 different priors for each theory, and then at the end you can have this figure where you have lines representing the probability of the theory given the data. So that's a kind of a nice way of, it's almost like a backup plan, because if people oppose the use of a prior because you're trying to apparently bias the data, because, but here's a sequence of priors that were used. So you not only have access to the model with the biased prior, you also see much weaker priors, and even like a reference level prior where it's like almost not informed that you can compare to. You can say, look, this one does a worse job explaining the data than this one, but it's all there. So there's no, you can't just say, oh, but you're reporting a model that, so that's a good point about sensitivity analysis, because it addresses the problem without actually getting rid of priors, but doing the opposite. So let me give you a bunch of priors that will be contradicting my own predictions, and we can compare them. So there's no, because in that scenario, you cannot say I'm using one prior that's biased. So it's one possibility to address the, but again, the question is always, what is the point of the study, right? Is this because that particular study there, the goal was to do that. The goal was to show, okay, how can we test different hypotheses in the model, and not just by collecting data, but doing both, right? Incorporating all of that. So that was the goal. So the work required to do the sensitivity analysis was, okay, yeah, that makes sense because that's the goal. But if it's just a normal paper, the question is, do you want to do all that just to circumvent a potential problem that you might have with the right? You probably don't want to do it. So that's what I mentioned before. Like, is there a good reason to use this type of model? Because if there isn't, if it's just because you like it, then sure, it will be a pleasure to work with the model, right? But then you have to be aware that you might actually have problems that you wouldn't have otherwise.
I don't think it's just a matter of like, would you enjoy doing this? And do you think it's worth doing? That's, I mean, I definitely think it is. It's more a question of like, what is the expectation around how much time you're able to put into a single paper?
Because a lot of the times you have convergence issues. So just to pick one reason, convergence, right?
Yeah.
Just to pick one reason, that is a good reason enough already to say, okay, yeah, let's just do this model instead, because then you won't have that problem. But then, yeah, there are things you have to adjust accordingly just to avoid having those types of questions and counter arguments and all that. And I think there needs to be some, depending on the journal, if it's a journal that already has a lot of papers written using this type of method, fine. If not, there's definitely need for a section explaining what this is and how to interpret the results and how different this is from a typical frequentist model.
Yeah.
So again,
that would be a very well-attended workshop at some future LabCon or something like that, just about deciding on priors. But the assumption that everybody is already familiar with the basics, like you presented today, but just take a few different problems in phonetics or laboratory phonology and actually figure out what the ideal priors are
and even not only the location of the prior, which in and of itself is most of the time what we would be doing. Like, where should the prior be along the scale given what I know about the literature,
Right,
but also the
exactly.
shape of the prior, right? Because let's say you have a situation where, so one obvious example is, okay, reaction times, right? So you could log transform it, or you can just use the log normal prior that will do that for you. But let's say you have a situation where you have a distribution like this, right? So is there a good, so first, is this expected? Did this make sense? So isn't it just a bug in the data or something? But you could technically fit anything, right? You could use whatever distribution is needed that is motivated, of course, in the prior. And of course, this is a weird scenario, but a lot of the times, the fact that we don't have to assume that things are normal is an incredibly important advantage. But most of the time, we don't use that advantage, right? Because what are, so that's another question. What are the scenarios where the distribution is not normal, but also not log normal? Is there a phenomenon that I'm interested in whose distribution is expected to deviate from the typical distributions? And that would be the perfect scenario to have one more very strong motivation to use this type of model, because you would be able to just, oh yeah, this is perfect. I can customize my model. And you have a lot of different differences in variance across groups, so yet another reason. So there's definitely a long list of reasons to use it, but there's always like a tiny price, or maybe not so tiny, for using that, right? And to consider what the packaging will have to be. Yeah. But it's there's a lot of stuff in there.
Do other people have questions? We should probably wrap up since we're already over time.
It was really helpful. Thank you so much.
Oh, good. Yeah, I'm glad it was helpful. The link is here.
Oh, yeah, could you
Oh, yeah.
send that to Ellie and she can
Sure.
put it around?
So this is the link for the OSF with all the material and links to the slides too. And this is the link to the, what is that? Oh, it's the continuation. So it's the figure that incorporates the random effects and all that, that manually extracts things and so on. Yeah, I can send it.
Thank you very much.
Thanks, Zoom people.
A little bit.